This tutorial video will be a discussion of Boyle's law, Charles' law, and Gay-Lussac's law. However, we can just keep things simple and think about solving all of these problems using the combined gas law. So for Boyle's law, we assume that temperature remains constant. So sometimes in the problem it will tell you that temperature remains constant. However, if the question doesn't say anything about temperature, you can assume that temperature remains constant. So essentially Boyle's law, temperature is constant, so if these were both the same, we could just cross them out. Okay, so the problem just becomes P1 V1 equals P2 V2. Okay, so let's solve this problem. A sample of oxygen gas has a volume of 150.0 milliliters when its pressure is at 0.947 atmospheres. What will the volume of the gas be at a pressure of 0.987 atmospheres if the temperature remains constant? Okay, sounds like a big scary problem, but again, with chemistry it's nice. We always have units attached to our numbers. So I see 150.0 milliliters and I know that that is going to be my volume. Okay, and the pressure is 0.947 atmospheres. Okay, what will the volume of the gas be? So we're looking for the new volume, V2, at a pressure of 0.987 atmospheres. Okay, so I'm given the pressure in atmospheres for both of these, so we do not need to do any kind of pressure conversion. These match. Previously, I told you that as long as the units match, it doesn't matter what they are except for temperature. Temperature is the only one that has to be in a particular unit, and that particular unit is Kelvin. So in this example, we are given the volume in milliliters, and that's okay. We do not have to do a unit conversion. We just know that our answer will also be in milliliters. So I'm going to go ahead and include the units when I'm solving this problem. Okay, so we have P1 V1 equals P2 V2. Okay, so I'm going to plug in my initial pressure. So it said 0.947 atmospheres and 150 milliliters. And then we are changing the pressure to 0.987 atmospheres. And we are looking for our new volume, which I will call X. Okay, so right away I can see that since I have atmospheres on this side of the equation and atmospheres on this side of the equation, we can just go ahead and cancel those out. Or if you think about it as dividing this one over to this side, okay, atmospheres divided by atmospheres, and your answer will be in milliliters. Okay, so if you convert milliliters to liters first, your answer would be in liters. Okay, either way, as long as you include your units in your answer, it would be correct. So 0.947 times 150 divided by 0.987. And I will get 143.9. Let's go ahead and round that to the correct number of sig figs. So my least number of sig figs is 3. So that will be 144 milliliters. Okay, again, if you had converted milliliters to liters first, your answer would be 0.144 liters, and either one of those would be correct. All right, so now let's move on to Gay-Lussac's law. Okay, so again, just think about it as using the combined gas law equation, except we will be omitting one value. Okay, combined gas law is a combination of these three laws that we're discussing. Okay, the gas in a container is at a pressure of 3.00 atmospheres at 25 degrees Celsius. Directions on the container warn the user not to keep it in a place where the temperature exceeds 52 degrees Celsius. What would the pressure in the container be at 52 degrees Celsius? So we are starting with 3 atmospheres. Okay, atmospheres is a unit of pressure, so I'm going to go ahead and label that as point P1, excuse me. And our temperature is 25 degrees Celsius, so it's 3 atmospheres at 25 degrees Celsius. So T1 is 25. Okay, for all gas law equations, we first need to convert this into Kelvin. So 25 plus 273 is 298 Kelvin. And we are looking at what will happen to the pressure if we get to 52 degrees Celsius. So our final temperature we're looking at is 52 degrees Celsius, which also needs to be converted to Kelvin. So 52 plus 273, and you will get 325. Okay, and we're trying to see what's going to happen to the pressure, so that is our unknown. Okay, so if we look at the gas law equation, okay, it doesn't tell us anything about the volume. Because volume is not mentioned in this problem, I'm going to assume that it remains constant. Okay, and it's in an enclosed container, so that should make sense. If the container is enclosed, the volume is not going to change. Okay, so we have P1 over T1 equals P2 over T2. So I'm going to plug in my values, 3.00 over 298. Okay, that was my initial pressure, initial temperature, and we are changing the temperature to 325. Okay, we're not sure about the second pressure, that's what we're looking for. All right, so now we can cross multiply. So I have 298 times x equals 3 times 325. We get 975. Now a reminder, most common mistake I see is students leave out x. If you forget about x in this step of the problem, it's very easy to divide the numbers the incorrect way. Okay, so since we want to get x by itself, I'm going to divide this side by 298 and this side by 298. So 975 divided by 298, and you will get 3.27. Okay, and we were looking for pressure. Since my initial pressure was in atmospheres, my final pressure will also be in atmospheres. Okay, and just like in the last problem, if you include the units at this step, you will see that you'll be left with atmospheres. Okay, and then for significant figures, my answer would have 2, because the least amount is 2. So 3.3 atmospheres would be your answer. Okay, one more problem. So Charles' law, again, we can just go ahead and use the combined gas law just to keep things simple. Okay, only one equation we have to deal with. So in this problem it says a sample of neon gas occupies a volume of 752 milliliters at 25 degrees Celsius. So I have an initial volume, okay, milliliters is volume, of 752. I have an initial temperature of 25 degrees Celsius, which is 298 Kelvin. What volume, so we're looking for the new volume, will the gas occupy at 50 degrees Celsius if the pressure remains constant? Okay, so in this question, if it didn't mention pressure at all, we could have assumed that, but I'm going to go ahead and cross that out of my combined gas law. Okay, if these are both the same, then they would just cancel out anyways. Okay, so final temperature is 50 degrees Celsius. So 50 plus 273, you will get 323 Kelvin. All right, so we're going to plug in the information into the equation. So we have V1, which is 752 milliliters. 298 Kelvin is my final temperature. Okay, so since I'm starting with milliliters, I know I'm going to end with milliliters. Okay, again, if you include the units, you can see how those cancel out. I'm going to leave them out just because it looks a little bit more confusing. Okay, so we're going to cross multiply 298x equals 323 times 752. Very large number, 242,896. Okay, I want x by itself. Divide both sides by 298. And my answer is 815, say 0.09. And since my starting volume unit was milliliters, my final volume unit will also be milliliters. Okay, to use correct number of significant figures, I'm looking back at the given information. This one only has one sig fig, so my answer will also have one sig fig. So 800 milliliters, or 8 times 10 to the 2 would also be acceptable answer.